So first off, developing your application. I'm going to talk about that in the context of cloud native, which is a really big term that's getting thrown around nowadays. And the official definition is here from the Cloud Native Computing Foundation, if you'd like to read it. But I think I've taken kind of some of the key parts of this definition, put them in bold, and these are some things that I think will lend to an application that is really going to benefit from the features that MiCADO has. So I've put in bold there: cloud, scalable, containers, and microservices, which are all big words right now. And if we kind of break those down, what we want to see eventually is an application that looks sort of like this purplish diagram on the right hand of the screen here. So we've got a cloud that can be a public cloud, a private cloud, or some mix of the two as a hybrid. And then we want our application to not be running as this kind of monolithic application that we've seen in kind of legacy software, but we want to implement a service-oriented architecture, or more specifically, a microservices architecture. So that's having many, many small components that are running together to serve the application. These microservices should ideally be running as application containers, which solve that kind of very long problem that it's been around for a long time of it runs on my machine, why doesn't it run on yours? And lastly, those containers, those microservices, should be scalable. So they should have some sort of not all of them, but some of them should have some elastic response to load. And if we have all of those things, we're going to be able to benefit from what's in MiCADO. Let's take a look at what each of those means in MiCADO and get a little bit more specific. So when we talk about a cloud in MiCADO, right now, as it is today, we talk about the clouds that we support. And those can be provisioned through Octopus, and we get access to OpenStack and Cloud Sigma and Amazon Web Services, or they can be indirectly provisioned through Octopus, but via the Cloud Broker platform, which gives us access to those same clouds plus Microsoft Azure. Currently, we're working on a future implementation where Terraform is also included in the architecture. And for anybody who knows Terraform, it's got a huge community behind it. There's lots of provisioners being written for it all the time as kind of new clouds are coming into the fore. And you can see that having Terraform as a tool will give us access to a lot of clouds. Next up, microservices. What are the kind of microservices that are really going to kind of benefit and work with MiCADO? Well, they need to be pretty resilient. So they need to be mostly independent of other services. They can't rely on one another to start up. There needs to be some fault tolerance there. While they should be independent, they should definitely and must usually have some sort of communication between one another. A really popular cloud native term for that right now is declarative APIs, but as long as there's some container communication happening, MiCADO can support that. And lastly, as many of these little microservices as can be should be stateless, because that makes it a lot easier to scale. That makes it a lot easier to update. Of course, at some point, you'll definitely want to persist some data as part of your application, and MiCADO has a number of ways of supporting that. But we kind of aim to have as many stateless components running in our application architecture as is possible. Lastly, or maybe not lastly, containers. When we talk about containers in MiCADO, right now we have support for Docker containers and Docker images. Those Docker images can be hosted in the official public Docker Hub, or they can be in your own private or custom hosted registries. That's fine. As I said, or as Joseph mentioned, we're doing our orchestration right now with Kubernetes. So if you've ever run an application on Kubernetes before, you can be pretty sure that it'll run really, really well in MiCADO. With Kubernetes coming in, we're planning to add support for the container runtime interface, which will give us access to a number of more runtimes and also those Open Container Initiative images. So we will be able to support more than just the standard Docker images. Last bit, and potentially one of the most interesting, is that your application or some part of your application should be scalable. So in MiCADO, we have kind of two very broad sections that we can split this into. One of them is scaling based on load, and this is really kind of a default that's included with MiCADO. MiCADO can monitor your hardware resources, so your CPU, your memory, or your network traffic, and then based on that metric passing a certain threshold, MiCADO can tell the application or the container to scale up or down. The other thing the other kind of solution we can have here is scaling to meet performance. And that's when all those nice custom exporters, custom Prometheus exporters that Josef mentioned come into play, and we can start to get really, really interesting with some of the metrics that we're watching. So maybe on a web server, we're watching the number of requests that are served per minute. Maybe we're watching the latency in a more experimental scientific setting where we're queuing a large number of jobs. Maybe we're fetching the number of jobs from the queue, the number of completed jobs for the queue, the average time. We can fetch all those as metrics and then use them to scale to meet whatever kind of performance or quality of service we've set out. So based on those four things, you now have a really, really great application that's ready to run in MiCADO. And the next thing you need to do is then describe that application in an ADT, an application description template, so that MiCADO understands how to run that application that you want. So ADT stands for Application Description Template. This is written in an OASIS standard specification called Tosca, which stands for the Topology and Orchestration Specification for Cloud Applications. It's a cloud language. It's written in YAML, so it's very, very readable. Generally, we like to think about MiCADO ADTs being authored by application developers or application owners. These are people who understand the application, they understand the metrics that are coming out of the application, and then how those metrics can be used to scale the various components and where the benefit is going to come in scaling those components. Of course, there'll usually be some final additions to be made by whoever's eventually launching this, as we can choose basically at deployment time which cloud service provider we want to use. So we're able to provide specific compute node instance details for a specific cloud service provider, having taken a general ADT that's been authored by some developer. There are three main sections to an ADT. The first is describing the container infrastructure, and that of course includes the containers, but can also include volumes or configurations that are a part of that. Second, to describe is the cloud infrastructure. So this is specific to the cloud service provider. What is the size of your instance or the type of your instance? Do you need to pass an SSH public key in? Do you have some firewall settings that you want to configure? And then what sort of a base virtual machine image do you want to use for this particular application? What OS do you want to be using? Last to describe are the policies. So the first is very simple, determining what sort of metrics we want to collect. And then the second, the scaling policy, obviously involves the scaling logic, where we set things such as thresholds, different alerts, the different queries, the different metrics we want to bring in, and exactly how we bring those in. We also here define the rules. So I'm going to show you some ADTs now, but in order to do that, I'd just like to preface it with our very favorite test application in MiCADO called stressng, which I'm going to use to run through a quick example ADT with you. Stressng is a little Linux tool which does some deliberate load testing on a system resource. Today we're going to use it to stress CPU in this example. It's already in a container on the public Docker Hub, so that's great, we can use it. We're using a small instance here from Cloud Sigma. We're going to enable the default metric collectors here to report and pull CPU usage so that we can monitor the CPU usage. And with that CPU usage, we're going to do some load-based scaling. So once the CPU passes above an upper threshold, we can scale up. And when it drops below a lower threshold, we can scale down. Very, very simple. So let's get on with it. Here's what an ADT looks like on the right side of the screen. Hopefully not too daunting. We give it a name. We provide it with a type. And this specific type, which you can see here, beginning tosca.nodes, describes a Kubernetes deployment, which is a very, very simple workload in Kubernetes. It's kind of the most basic scalable workload in Kubernetes, let's say. And to that type, we provide some additional properties. And these are the properties that are going to distinguish our application or this one container from just a kind of typical Kubernetes deployment. So we provide the container image we want. We provide any options or parameters that need to be sent to the container. And here we're also defining some resources, which are going to limit the number of containers that can run per virtual machine. If these fields look a little bit similar because you've been working with Kubernetes a lot, they should. These are taken straight from a Kubernetes manifest, and generally an ADT will accept most of the properties that are available in Kubernetes. Next up, it's time to describe the cloud infrastructure. Should look pretty similar to the last description we saw. Again, we give it a name, we give it a type. Obviously, the type here is different. We're not describing a container or a Kubernetes workload. We're describing a cloud compute instance. So this is a specific type for a Cloud Sigma instance orchestrated by Octopus of a small size. In addition here, we have to provide those kind of specific cloud service provider input. So the drive image, that's the base image we said. Cloud Sigma requires us to pass in a public SSH key, and we can also define some open ports or a firewall policy here if we want to. Last up to describe are the policies themselves. We split these into two. Very simply, the monitoring policy just has some flags either on or off, so we can either enable the container and node metrics, or we can disable them. The scaling policy is a little bit more involved. It takes a type, but it also takes some targets. So these targets are other nodes or other containers that we've described elsewhere in this ADT that we want this particular scaling policy to affect. As well as these targets, we provide some constants, which in this case are a couple of thresholds, and we provide some limits. So those are the upper and lower bounds on how far we want this particular stressng instance to scale up and down. And then we'd have another scalability policy to follow that, which would target the compute nodes. Obviously, there's a bit of magic going on here because certainly there needs to be some scaling logic somewhere, and that's kept in what we call a policy type definition. So these policy type definitions are generally referenced in the ADT, just as we saw. They're authored by application developers or even policy developers, individuals who really understand the kind of alerting and querying magic that exists behind Prometheus. So you can see here, if you're familiar with Alert Manager, which is a Prometheus tool, you can see we're just generating some alerts based on Prometheus queries. When those alerts fire, you can see down at the bottom section the scaling rule, which is that Python logic that Joseph mentioned, and you can see very simply, in a very simple, this is a very simple example, but you can see in a very simple Python script, we catch those alerts as they're being fired, and if conditions are met, we can increase the container count by 1, and if underloaded conditions are met, we can decrease the container count by 1. So I'm sure you've had enough of kind of looking at these ADTs, and you want to see how an application actually runs. So that'll be on to the next two sections. So thank you very much for listening.